Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime, Series 24, Episode 104, for broadcast on the 15th of September 2021. Coming up on SpaceTime, fast radio bursts traced down to galactic spiral arms. How big does a star need to be to form a stellar mass black hole? And new evidence shows the solar wind slowing down beyond Pluto. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers using NASA's Hubble Space Telescope have traced the locations of 5 fast radio bursts to the spiral arms of 5 distant galaxies. Fast radio bursts are sudden ephemeral blasts lasting just a nanosecond, but releasing more energy in that time than the Sun does in a whole year. The explosions occur at very specific wavelengths, and usually at cosmic distances. The first was discovered back in 2007 in data from the Parkes Radio Telescope in rural New South Wales. Since then, hundreds more have been detected. The first bursts all seem to be singular events, occurring just once at a specific location and then never again. And that suggested they were being caused by some sort of cataclysmic event such as a supernova. But not long afterwards, astronomers began detecting fast radio bursts that were repeating from the same location. And that suggests a different cause. The leading contender is a highly magnetized neutron star called a magnetar. But feeding black holes and glitching neutron stars haven't been totally ruled out yet. The new findings, reported in the Astrophysical Journal, are consistent with the idea that fast radio bursts originate from young magnetars. Now, if so, it means there could be 2 separate causes for these mysterious deep radio blasts. Or it could be that all fast radio bursts are repeaters, with some just being a lot more active than others. Because of their extremely short duration, astronomers have had a hard time tracking down exactly where fast radio bursts come from, much less determining what kind of object or objects are causing them. Because of this, most of the time, astronomers don't really know exactly what to look for. Locating where these blasts are coming from, and in particular what galaxies they originate from, is important in determining exactly what kind of astronomical events are likely triggering these intense flashes of energy. And that's where this new Hubble survey of fast radio bursts comes in, helping astronomers narrow down the list of possible sources. The study's lead author, Alexandria Mannings from the University of California, Santa Cruz, says the new Hubble results are exciting because they're the first high-resolution view of a population of fast radio bursts, and Hubble localizes them to near or on a galaxy's spiral arms. Interestingly, most of these galaxies are massive, relatively young, and still forming stars. The Hubble data allows the authors to get a better idea of the overall host galaxy's properties, such as its mass, its star-forming rate, as well as probe what's happening right at the fast radio burst position. The galaxies in the Hubble study are all billions of light years away, and so they're being seen as they appeared when the universe was about half its current age. Many of these galaxies are as massive as the Milky Way. The observations were made in ultraviolet and near-infrared using Hubble's Wide Field Camera 3. The ultraviolet light traces the glow of young stars strung along the spiral arms of the galaxy, and the infrared images help calculate the galaxy's mass and determine where the older stellar populations reside. The images display a diversity of spiral arm structure, from tightly wound to more diffuse, revealing how the stars are distributed along these prominent features. A galaxy's spiral arms trace the distribution of young massive stars. The Hubble images revealed that the fast radio bursts found near the spiral arms don't come from the very brightest regions, which are blazing with light from hefty stars. And that supports the view that fast radio bursts don't originate from the youngest, most massive stars. So these clues have helped the authors rule out some possible triggers for these bursts, including the explosive deaths of the youngest, most massive stars, which generate gamma ray bursts and some types of supernovae. Another now unlikely source is the merger of two neutron stars, the crash cause of stars that end their lives in supernova explosions. These mergers take billions of years to occur and are usually found in the spiral arms of older galaxies, ones that are no longer forming new stars. Importantly, last year astronomers linked observations of one fast radio burst spotted in our own Milky Way galaxy with a region where a magnetar is known to reside. Magnetars generate powerful flares and magnetic processes on their surface, which can emit radio energy. And these new observations also help strengthen the association of fast radio bursts with massive star-forming galaxies. Although the Hubble results are a major piece in the puzzle, the authors say they still need more observations in order to develop a more definitive picture of these enigmatic flashes and better pinpoint their sources. This report from NASA TV.
Fast radio bursts, or FRBs, are extraordinary events that generate as much energy in 1,000th of a second as the sun does in an entire year. Astronomers using NASA's Hubble Space Telescope have traced the locations of 5 brief, powerful radio blasts to the spiral arms of 5 distant galaxies. Because these radio pulses disappear in much less than the blink of an eye, researchers have had a hard time tracking down where they come from and what causes them. Locating the galaxies where these blasts originate is important in determining what astronomical events trigger such intense flashes of energy. The Hubble Space Telescope helped researchers narrow the list of possible FRB sources. Since their discovery, astronomers have uncovered up to 1,000 FRBs, but only about 15 are associated with particular galaxies. In this new Hubble study of FRBs, astronomers pinpointed where those bursts occurred within their specific galaxies. These images display a range of spiral arm structures, from tightly wound to more open, revealing how stars are distributed along these prominent features. These clues helped researchers rule out some of the possible stellar objects originally thought to cause these brilliant flares, including the explosive deaths of the youngest, most massive stars, which create gamma ray bursts and some type of supernova. Another unlikely source is the merger of neutron stars, the crushed cores of stars that end their lives in supernova explosions. These mergers take billions of years to occur and are usually far from the spiral arms of older galaxies that no longer form stars. This study suggests that FRBs do not originate from the youngest, most massive stars or from older stars in a galaxy's central bulge. However, it is consistent with the leading model that FRBs originate from young magnetar outbursts. Magnetars are a type of neutron star with powerful magnetic fields. Called the strongest magnets in the universe, magnetars possess a magnetic field 10 trillion times more powerful than the magnets on your refrigerator door. These magnetic fields lead to flares and magnetic processes that can emit radio light. Although the Hubble results are exciting, researchers need more observations to better pinpoint the source of FRBs so they can develop a stronger understanding of these enigmatic flashes. This field of study may need a lot more research, but thanks to observations made with the Hubble Space Telescope, we're getting closer to understanding the mysteries of the universe.
This is SpaceTime. Still to come, how big does a star need to be to form a black hole? And a new study shows the sun's solar wind is slowing down beyond Pluto. All that and much more still to come on SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
A new study suggests the upper mass limit for a core collapse supernova might be far lower than previously thought. The findings, reported in the Astrophysical Journal and on the pre-press physics website archive.org, propose that progenitor stars greater than 23 to 27 solar masses don't explode as core collapse supernovae, but instead collapse directly down to form a stellar mass black hole. Stars shine by fusing hydrogen in their core into helium, releasing energy in the process. And once they run out of core hydrogen to fuse, they'll start fusing the helium they've just created into carbon and oxygen. But eventually the helium will run out too. Stars like our Sun aren't massive enough to fuse carbon and oxygen into heavier elements, and so they end their lives as slowly cooling stellar corpses called white dwarfs. But far more massive stars, with stellar cores greater than about 1.44 times the mass of our Sun, that Chandrasekhar limit we talked about earlier in the week, can generate far higher pressures and temperatures, allowing them to fuse elements through a different process, and thereby generate progressively heavier and heavier elements until eventually they can produce iron in their core. But the thing is, no matter how massive a star gets, it can't produce the sorts of core temperatures and pressures needed to fuse iron into heavier elements. And so the balancing act between the inwards pull of gravity crushing a star down towards its center and the outwards push of energy caused by nuclear fusion comes to a final end, and gravity wins, causing the star to collapse catastrophically, crushing the core and triggering a core collapse supernova. The force of this collapse is so enormous, it forces the core's negatively charged electrons and positively charged protons together, forming neutrons, and producing one of the most exotic objects in the universe, a neutron star. However, astronomers have recently estimated that stars with cores greater than around 2.2 to 2.3 solar masses would collapse beyond the neutron star stage, forming the strangest objects in the known universe: black holes. Those points of infinite density and zero volume we discussed earlier in the week. It's long been hypothesized that a star collapsing into a black hole might not generate a visible core collapse supernova. That's because the black hole's event horizon would limit the amount of material available to escape. But the thing is, current models suggest that core collapse supernovae would occur in stars up to around 40 or 50 solar masses, above which they would collapse directly into a black hole without generating a supernova. The models also predict that extremely massive stars, those 150 solar masses or more, would explode through a different process known as a pair instability supernova, where colliding photons created in the core generate pairs of electrons and their antimatter counterparts, positrons, which then proceed to annihilate. The new findings suggest that progenitor stars greater than 23 to 27 solar masses would have enough mass to collapse directly into a black hole. That's far smaller than previously thought. It also means there are probably far more black holes out there than previously thought. The authors reached their conclusions by studying the elemental abundances of a pair of colliding galaxies known as ARP 299. The merging galaxies are triggering a huge amount of stellar activity, including both starburst, that's the formation of lots and lots of new stars, and also supernovae, the death of stars. This increased number of supernova events means higher abundances of the elements generated by such events. So, the authors decided to measure the ratios of iron to oxygen and those of neon and magnesium to oxygen, finding that the neon-magnesium ratios were similar to the Sun, while the iron to oxygen ratio was much lower than solar levels, even though large amounts of iron should be generated through core collapse supernova explosions. Interestingly, the data matched models which excluded stars greater than 23 to 27 solar masses, and that suggests a lower limit for when a progenitor star collapses directly into a stellar mass black hole, rather than forming a neutron star. This is SpaceTime. Still to come. New measurements show the solar wind slows down beyond Pluto. And an experimental new rocket crashes and burns during its launch. All that and more still to come on SpaceTime. New measurements by NASA's New Horizons spacecraft have confirmed earlier data showing that the solar wind, the supersonic stream of charged particles emitted by the Sun, slows down the further away it gets. The findings, reported in the Astrophysical Journal, are providing important new insights into some of the furthest reaches of space ever explored. Previously, only the 1970s vintage Pioneers 10 and 11 and Voyagers 1 and 2 spacecraft have explored the outer solar system and furthest reaches of the heliosphere, the bubble created by the Sun's atmosphere, which encompasses the entire solar system. But now New Horizons, using far more modern technology, is doing the same thing. The study's lead author, Heather Elliott from the Southwest Research Institute in Boulder, Colorado, says the Sun's influence on the space environment extends well beyond the outer planets, and New Horizons is showing new aspects of how that environment changes with distance. The probe is collecting detailed daily measurements of the solar wind, which is composed primarily of ionized hydrogen, in other words, free protons and electrons, as well as helium nuclei known as alpha particles. And there are trace amounts of heavy ions and atomic nuclei, including carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and iron, ripped apart by the extreme million-degree temperatures in the Sun's outer atmosphere, the corona. New Horizons is also collecting data on other key particles known as interstellar pickup ions in the outer heliosphere. Now, these interstellar pickup ions are created when neutral material from interstellar space, that is the space beyond our solar system, enters the solar system and becomes ionized by light from the Sun or by charge exchange interactions with solar wind ions. As the solar wind moves further from the Sun, it encounters an increasing amount of material from interstellar space. When interstellar material is ionized, the solar wind picks up this material and, researchers theorize, slows down and heats up in response. And New Horizons has now detected and confirmed this predicted effect. The authors compared the New Horizons solar wind speed measurements from 21 to 42 astronomical units with the speeds measured at just 1 astronomical unit out, recorded by both the Advanced Composition Explorer or ACE spacecraft and the Solar Terrestrial Relations Observatory or STEREO spacecraft. By the way, an astronomical unit is the average distance between the Earth and the Sun, which is roughly 150 million kilometres or 8.3 light minutes. By 21 astronomical units, it appeared New Horizons could be detecting the slowing of the solar wind in response to picking up interstellar material. However, when New Horizons travelled beyond Pluto, between 33 and 42 astronomical units out, the solar wind measured 6 to 7% slower than what it was at 1 astronomical unit distance, confirming the effect. In addition to confirming the slowing of the solar wind at greater distances, the change in solar wind temperature and density also provides a means to estimate when New Horizons will join the Voyager spacecraft on the other side of the termination shock. That's the boundary marking where the solar wind slows to less than the speed of sound as it approaches the interstellar medium. The Voyager 1 spacecraft crossed this termination shock in 2004 at 94 astronomical units out. It was followed by Voyager 2 in 2007 at 84 astronomical units. Based on the current lower levels of solar activity and lower solar wind pressures, the termination shock's expected to have moved closer to the Sun since the Voyager crossings. Now, extrapolating current trends in the New Horizon measurements also indicates that the termination shock might be closer now than what it was when intersected by the Voyagers. Scientists estimate that at the earliest, New Horizons will cross the termination shock during the mid-2020s. But as the solar cycle activity increases, the new increase in pressure will likely expand the heliosphere. And this could push the termination shock back out to around 84 to 94 astronomical units, the same range as found by the Voyager spacecraft. And it could reach this distance before New Horizons has time to reach it. New Horizons' journey through the outer heliosphere contrasts with that of the Voyager's, in that the current solar cycle is mild compared to the very active solar cycle the Voyagers experienced in the outer heliosphere. In addition to measuring the solar wind, New Horizons is extremely sensitive and simultaneously measures the lower fluxes of interstellar pickup ions with unprecedented time resolution and extensive spatial coverage. Also, other than the Juno spacecraft, New Horizons is also the only spacecraft in the solar wind beyond Mars, which is roughly 1.5 astronomical units out from the Sun, and consequently the only spacecraft measuring interactions between the solar wind and the interstellar material in the outer heliosphere during the current mild solar cycle. If all goes well, New Horizons is on course to become the first spacecraft to measure both the solar wind and interstellar pickup ions at the termination shock. We'll keep you informed. This is SpaceTime. Still to come, an experimental new rocket crashes and burns during launch from the Vandenberg Space Force Base. And later in the science report, climate change starting to show its effect on the genetic diversity of polar bears. All that and more still to come on SpaceTime. An experimental new rocket has crashed and burned during its launch from the Vandenberg Space Force Base in California. The 26-metre tall Firefly Alpha suffered a sudden engine shutdown on one of its 4 main first-stage motors 15 seconds after launch. The 2-stage rocket continued to climb on its remaining 3 first-stage engines, but ultimately failed to maintain control and tumbled out of the sky 45 seconds into the mission, triggering a self-destruct over the North Pacific Ocean. The cause of the rocket motor shutdown was a propellant main valve failure on the number 2 engine. The Alpha is being developed to launch 1,000-kilogram payloads into low Earth orbit. That puts the company in direct competition with New Zealand's Rocket Lab, which has already placed 105 satellites into orbit, and Virgin Orbit, which has sent 17 satellites into orbit aboard 2 flights using its Launcher 1 rocket, which is drop-launched from beneath the wing of a specially modified Boeing 747 airliner. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study claims the Moderna vaccine, which arrives in Australia this week, generates higher antibody levels than the existing mRNA vaccine produced by Pfizer. The findings, which were reported in the Journal of the American Medical Association, are based on a new Belgium study which included people who had previously tested positive for COVID-19, along with those who had not been infected, and found higher antibody levels in both groups. The authors say the higher mRNA content in the Moderna vaccine and the longer interval between doses, 4 weeks as opposed to 3 weeks for Pfizer, might explain this difference. But whether this difference translates into a difference in duration of protection against different variants of the virus, and the risk of transmission still needs to be further investigated. Meanwhile, a US study warns that COVID-19 may be more transmissible in households than previously thought. The findings, reported in the Journal of the American Medical Association, brought together data from 37 separate studies, together with a further 50 studies they had previously analysed, representing a total of around 1.25 million households in 30 countries. The authors found that overall, the estimated chance of passing COVID-19 to another household member was around 18.9%. That's far higher than the previous estimate of 16.6% from the original 50 studies. However, researchers also found that when household members had other existing illnesses, they had a 50% higher chance of catching COVID-19 in their homes. And when looking at just the alpha COVID-19 variant, transmissibility was also higher at 24.5%. The World Health Organization says more than 8 million people have now been killed by the COVID-19 coronavirus, with over 4.6 million confirmed fatalities and some 230 million people infected since the deadly disease first spread out of Wuhan, China. A new study has shown that climate change is starting to affect the genetic diversity of polar bears as Arctic ice melt limits their range and consequently their ability to interbreed. The findings, reported in the Proceedings of the Royal Society B, analysed the genetics of more than 600 polar bears from the Svalbard archipelago in Norway. Scientists found a 3 to 10% loss in genetic diversity among polar bears between 1995 and 2016. The researchers say the change in diversity could be explained by a loss of ice coverage in the region, leading to greater inbreeding as it becomes harder for polar bears to move from one location to another. Well, he weighed 7.5 tons and was over 14 metres long, but it seems Tyrannosaurus rex was not a huge beast gobbling everything in sight. Instead, Japanese researchers say T-Rex likely had very sensitive jaws that could recognise different parts of their prey. The researchers found that the nerves in the lower jaw of a T-Rex were distributed in a far more complex fashion than those of any other dinosaur. In fact, they were comparable with those of modern-day crocodiles, another member of the Archosaur family, and as tactile as some foraging birds, which are known to have extremely keen senses. The findings, reported in the journal Historical Biology, could mean that in addition to hunting and eating, T-Rex's lower jaw tips could have been adapted to perform a series of behaviours with fine movement control, including nest construction, parental care, and even interspecific communications. There are warnings today about a new set of Bluetooth malware collectively known as Bracktooth. With the details, we're joined by technology editor Alex Zaharov-Reutt from ITWire.com.
Yeah, it's called Bracktooth, and it was discovered by the Singapore University of Technology and Design. And it is a way of hacking into Bluetooth. Now, Bluetooth is obviously used in many different devices, from smartphones and computers and tablets through to Internet of Things devices. And what this vulnerability can do is allow arbitrary code execution on affected devices. Now, arbitrary code execution means that people can install code to run on systems that you might not wish to have code running on that isn't authorized by you. Now, just quickly, Bracktooth, the word brack is from the Norwegian and translates to crash in English, and tooth points towards Bluetooth.
Now, the thing about Bluetooth is it usually only works at very close ranges, doesn't it?
Yeah, Bluetooth is normally only about 10 meters. I mean, there are certain devices that claim to work a bit longer than that, but normally Bluetooth is short range. But there are 1,400 different models of commercial products that have Bluetooth, laptops and cars and commercial aircrafts, heavy trucks, all sorts of things. At the moment, most of the Bluetooth devices that are out there have drivers from Intel or Qualcomm or Texas Instruments or other organizations. And there are various patches that are being written for these different devices. Not all of the devices have had patches written yet, and you'll probably find that your Windows update or the updates for your various devices will offer updates to fix this, but not everything is going to be updated. Texas Instruments says that it will consider producing a patch only if demanded by customers. And Qualcomm has also reportedly patched the flaws in some of its devices, but there are some devices that they have no plans to patch. So this is where it's always important to make sure you are running the latest software updates or firmware updates, and if something is vital and there are no updates, then you have to replace it. Because if a company is not going to update it, then that can potentially lead to a way of the bad guys breaking into systems, and sometimes in things that in theory you wouldn't think would be vectors of hacking into a network.
That's Alex Zaharov-Reutt from ITWire.com. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.